This is Dr. Anthony Filippi, faculty member in the Department of Geography here at Texas A&M University in College Station, Texas. And the topic of this lecture is on aerial photography. And specifically, I'll be focusing on the concept of vantage point. I will be discussing different types of camera systems that are used in aerial photography, as well as different types of filters and film and how they work. Much of what I will be focusing on here will be specific to film or analog based aerial photography. However, some of what I will be discussing are either specific to digital photography or will be cross applicable to both analog or film based photography as well as digital photography. Now, even though much of aerial photography has gone over to the digital domain in recent years, having a solid understanding of film or analog-based aerial photography will always be important in remote sensing because we have built up over many decades a very extensive image archive based on film or analog-based aerial photography. So we really need to understand how it works in order to properly interpret that long-term image archive. Now, the satellite remote sensing record goes back a handful of decades. We can, and that would be the satellite archive focused on Earth resource remote sensing. We can extend that further back a couple of more decades into the 1960s and back into the 1950s if we utilize declassified Corona and other intelligence satellites declassified from the Cold War period. However, if we want to extend our remote sensing image acquisition archive back even further, then we need to utilize aerial photography. And in some parts of the world, we started collecting aerial photography, maybe as far back as the 1920s or 30s. It varies in different parts of the world, but generally within the United States and various other countries, we've had a pretty continuous aerial photographic image archive over the decades since then, where aerial photographic missions have been conducted on at regular intervals on a regular basis. So if one wanted to conduct long-term multi-temporal analyses of, say, for example, land use, land cover change over time, we really need to or we would often be utilizing this extensive aerial photography archive, much of it based on analog or film-based camera systems. So with that, we'll start looking into these various issues in the subsequent slides. Multiple important issues will be discussed here, which include the notion of vantage point, and specifically I will be distinguishing between vertical aerial photographs as well as low and high oblique aerial photographs. Also, the camera system that is being deployed is important, and I will break this down into metric versus panoramic camera systems. Filtration is another important topic, and so I'll be discussing different types of filters that can be used in aerial photography, haze, minus blue, bandpass filters, etc. And finally, film emulsion. So various types of film emulsions can be utilized, including black and white films, black and white infrared, color, and color infrared film. So I'll be discussing these various film emulsions and how they work in the subsequent slides. Here we can very clearly see the effect of utilizing different types of film emulsion in aerial photography. So on the left-hand side we have an example panchromatic aerial photograph, and on the right-hand side we have a black and white aerial photograph. Both of these are acquired over the same geographical area and were acquired at the same time. Again, this is a wetland area of the Hudson River, and we see wetland vegetation that are included in these photographs, as well as an aquatic area. And because we are, in the case of the panchromatic image, we are integrating photons over a very wide spectral range. The photons that are impinging on our film surface are over, typically, say, over the entire visible portion of the spectrum. We're actually able to interrogate the water column much more readily than what we see over on the right-hand side. in the case of near infrared radiation, much of that radiation is going to be absorbed by the water, and so we don't actually see a lot of detail in terms of the constituents of the water body. Looks basically black in the black and white infrared photograph in this case. However, again, the vegetation, and this is to varying degrees, of course, depending upon whether or not we're looking at marsh grass or deciduous forest. We have those various vegetation types within the study area. But we see varying degrees of relatively bright reflectance values, and hence bright shades of gray, bright tones, if you will, in the black and white photograph where we have vegetation. In the panchromatic, again, we have greater amounts of absorption in the visible portion of the spectrum by vegetation. And although we have the highest reflectivity in the green, the magnitude of the reflectivities in any portion of the visible portion of the spectrum does not approach the magnitude that we see in the infrared portion of the spectrum. So that accounts for the darker brightness values that we see in the panchromatic for the vegetated areas versus what we see in the infrared photograph. I will now show a short series of photographs, a few photographs here in sequence, whereby the vantage point from which these photographs were acquired varies. And think about what differs from one photograph to the next, besides the nature of the target. The exact study area that is contained within these photographs are different, but that's not what I'm really wanting you guys to focus on in terms of the differences between these photographs. So this is what is referred to as a low oblique aerial photograph. This is an example of what we refer to as a high oblique aerial photograph. And this is an example vertical aerial photograph. So think about what is different from one photograph to the next in terms of what is included in each one of these images. So for vertical aerial photography, this is a profile schematic diagram of the image acquisition process. We have our camera system mounted on an aerial platform. We have a field of view and an angle that describes that field of view, the angle over which we are accepting photons into our camera system. We have an optical axis that extends directly down from the aircraft, perpendicularly intersecting a flat level terrain, forming ideally a 90-degree angle, and the principal point would be located at that point. And we would describe the altitude of the aircraft at the time of image acquisition by an altitude above ground level or an altitude above sea level. And that extends from the ground surface up to the film plane of our camera system. A vertical aerial photograph is obtained when the camera's optical axis, again this imaginary line that extends down from our camera system and intersects with the Earth's surface, if that axis is within plus or minus 3 degrees of being vertical or perpendicular to the Earth's surface. And if we have overlapping vertical aerial photographs such that those photographs overlap to a sufficient degree and such that we are acquiring imagery of the same portion of the Earth's surface from slightly different viewing positions or vantage points, we may then analyze those overlapping vertical aerial photographs photogrammetrically in order to derive accurate planimetric XY location base maps, topographic base maps, so we could extract out Z elevations above sea level, for example in the form of topographic contour lines or digital elevation models. And we can also construct accurate orthophotographs, which are basically aerial photographs that are geometrically accurate in the XY, so they have been corrected for topographic variability. And all of these photogrammetrically derived data sets are widely used in a geographic information system setting. So we can use them in concert with other spatially registered data layers to perform potentially complex spatial or spatiotemporal analyses. An oblique aerial photograph is one where the camera's optical axis deviates more than plus or minus 3 degrees from vertical. Now, there are some advantages with oblique aerial photography in that we can potentially see the sides of some objects. So that could yield structural information about various types of objects. However, it's often disadvantageous in that scale is not constant throughout an oblique aerial photograph, and so if we want to make metric measurements, area, distance, perimeter measurements, things of that nature, based on our aerial photography, we would usually want to utilize vertical aerial photographs to the greatest extent possible. Now, there is a distinction between different types of oblique photography. A low oblique aerial photograph is one where the horizon is not visible, whereas a high oblique aerial photograph is where the horizon is visible. So whether or not the horizon is visible is the distinction between low and high oblique aerial photographs. It should also be noted that for image interpretation purposes, the analyst should always orient the oblique photograph such that features of interest appear in a basically natural perspective. So if we have objects with some height above the local datum, we would want those objects to appear to lean away from the observer's vantage point. Otherwise, that could potentially complicate the interpretation of the image. And this is just a graphical depiction of what we were talking about. So on the left-hand side, we see a profile view of the aerial photography acquisition process where we have an off-nadir optical axis. We are greater than plus or minus 3 degrees off of vertical. However, the horizon is not visible within the photograph that appears over on the right-hand side of this figure. And this is an example of the data collection scenario for a high oblique aerial photograph, whereby we have a more extreme deviation from the vertical for our optical axis. And the horizon is visible in these types of images, which we see over on the right-hand side of this figure. Again, note that the scale variability that we have from the foreground of the image is markedly different from the scale within the image in the background part of the image. So again, if we want to make accurate metric measurements about the area of various objects or the perimeter of objects, distance measurements, etc., we're really going to want to use a vertical aerial photograph for those purposes. But again, one of the advantages of this type of photograph is that we can see quite a bit of information about the sides of various objects, the side of the bridge, the side of the dam. That might be useful for infrastructure inspection purposes. You could also imagine various other types of applications, maybe in a military application domain, whereby maybe you see a linear feature in a vertical aerial photograph that may be difficult to interpret, but if we had a high oblique image of such a linear feature, then it may become clear that maybe it's a wall that may prohibit movement of troops or something like that. So again, for some purposes, it can facilitate the image interpretation process, but for certain types of measurements, its utility may be limited. This is just a simple box camera. This is one of the first commercially available box cameras created for Louis Daguerre by Samuel F.B. Morse. He's the inventor of the Morse code, but he also invented this simple camera system. Interestingly, there are many comparisons to be had and many similarities between the human eye and a basic camera system. And that's basically what we see here in this diagram. In the upper portion of the diagram, we have a schematic diagram and profile view of the image acquisition process for the human eye. And similarly, we have that same sort of diagram, but for a basic camera system. In this case, it is a film-based or analog camera type of a system. In the upper portion of the image, we have an illumination source. This isn't shown, but implicitly, this is what is going on. We have an illumination source. Usually that's going to be the sun that is illuminating the terrain and various objects on the terrain with photons. Some portion of those photons are going to be reflected into the direction of our observer. Those photons will then pass through the lens of the human eye, and in so doing, we'll have a reversal in the geometry of that object. In this case, it's a tree. And the image of that tree is actually going to be reversed then. It'll appear upside down on the back part of the human eye, which is where we have the retina. It's the human visual cognitive system then that reverses that geometry again, such that various features appear in their proper geometric configuration. So the tree, as we view it, cognitively would appear as being upright. But within the human eye, at the retina, when we are imaging objects, it's actually upside down. And if we look at the bottom portion of this figure at the camera system, we have the same phenomenon occurring. So we have our object, those photons that are being reflected from that object passing through the lens. We have a reversal in geometry of that object at the back of the camera, where we have the film plane, and the film plane is analogous to the retina in the human eye. Also note we also have a lens for our camera system on the bottom portion of this figure. And we also have an aperture that serves a function very similar to the iris that we see in the upper portion of the image of the human eye, which is basically controlling the illumination or the photons that are passing through the lens and ultimately impinging on the retina, or in the case of the camera system, that are impinging on the film plane. So to summarize the comparison between cameras and the human eye, we have the light-sensitive retina in the human eye that is analogous to the light-sensitive film that is located at the film plane, located at the back of the camera. Both the human eye and the camera system have a lens, and the function of that lens is to focus reflected light onto the retina or onto the film plane. We also have the iris that exists within the eye, and that controls the amount of light that is used to reach or illuminate the retina. And also we have an eyelid, and that acts as a shutter, which is what a camera system would have. In a camera system, the amount of light that is actually going to reach the film plane is going to be controlled by a couple of things. One, the size of our lens aperture opening, and number two, a shutter, which is going to control the length of time or the exposure that the lens aperture remains open, that is going to allow light to pass through or photons to pass through. We should also note that the shutter can be placed in the camera lens assembly, or it could be placed just in front of the film plane at the back of the camera. In that particular case, the latter case, we would refer to that type of shutter as a focal plane shutter, because it would be located just in front of the film plane. And to more precisely define that term, note that the film plane, or what we also sometimes refer to as the focal plane, is where the film is located at the back of the camera. And it's also the area where the film is being held flat during the exposure process. Another term to be familiar with is the focal length. That is a very important parameter for aerial photographic systems, and that is the distance from the rear nodal point of our lens to the film plane. And some common focal lengths for various mapping systems are as follows. 88 millimeters or 3.5 inches, 152 millimeters or 6 inches, 210 millimeters, 305 millimeters or 12 inches, and so on. There are others, but these are some of the more common ones. Metric cameras that we use for typical mapping purposes usually have a fixed focal length of 152 millimeters or 6 inches rather than a zoom type of a lens. A zoom lens would have a constantly changing focal length, but again, usually for metric-based mapping from a aerial photographic platform, we again are typically going to have a fixed length camera, and often it's of 6 inches in length. Although, again, there is possible variability in terms of focal lengths. In general, we would want a longer focal length for high altitude type of mapping purposes. And this slide just shows various diaphragm aperture stops. On the left-hand side, we see a perspective view The middle figure is a narrow aperture, and on the right-hand side is a figure of a wide aperture. So the wider aperture, of course, is going to let in more light. It's going to allow more photons to pass through into our camera system, ultimately impinging on the film plane. And a narrow aperture thereby is going to let fewer photons or less light to pass through. An important concept in aerial photography image acquisition is that of f-stop, and that is computed with this equation here. So it is simply f over d. In f, little f there is the focal length, and little d is the diameter of the lens opening. So we just take focal length divided by that diameter, and the f-stop is used to specify the speed or the relative aperture setting. So for example, if we have a focal length of 100 millimeters and we have a maximum lens diameter opening of 10 millimeters, which we would call full aperture, if that's our maximum lens diameter opening, we would say then that we have an f10 lens. And where do we get that? Well, we take 100 millimeters divided by 10 millimeters. Another example would be if we have 100 millimeters divided by 20 millimeters, we would have an f5 lens. So the smaller the f rating, the faster the lens system that we have. Or you could think of that as being the more light that's going to be admitted or be allowed to pass through the lens opening per unit time. So for example, if we have an f5 lens, that would be faster than an f10 lens. So the greater the f-stop, the less light that's going to be admitted. And aerial photographic systems typically have very fast lenses because, well, aerial platforms are usually going to be moving, potentially moving at a relatively high speed, unless it is a tethered sort of platform. Say it's a tethered balloon or something. But generally, if it's an aircraft-based system, again, we're going to want to have a very fast lens. Why? Well, fast lens will tend to stop action, and we don't have then kind of a smearing effect. We would certainly want to avoid that. And fast lenses are often used with very sensitive types of film. So really we have a system of apertures beginning at f1 that can be produced by multiplying any aperture by 1.4142136, which is the square root of 2, and that is going to produce the succeeding smaller aperture. So for example, the sequence of full stop increments would be f1, f 1.4142, f 2.828, f4, f5.656, and so on. You see the progression there. So each lens in that series is transmitting half as much light as the preceding lens opening. So for example, an f8 lens is going to be transmitting half as much light as an f5.6. So, we would stop down, quote unquote stop down, that would be the term, from f11 to f16 in order to decrease the aperture lens opening and the amount of light that is reaching the film plane by 2. So in this table we see the international series of f-stops and shutter speeds. In the upper progression of numbers we see the relative aperture of f-stops. On the left hand side we have larger lens openings, on the right hand side we have smaller lens openings. So larger lens openings would be lens openings such as f1 or f2, smaller lens openings would be f22, f32, and so forth, so on. On the bottom portion of this table are the shutter speeds. On the left-hand side are slower shutter speeds, faster shutter speeds are on the right-hand side. And lens speed is the F number of the maximum effective diameter of the lens when the diaphragm is wide open, or what we call full aperture. And what we see here are the f-stops for a camera lens and the size of the aperture openings. So the size of the aperture is shown by the white circles, and the lowest f-stop has the largest opening and lets in the greatest amount of light. So the greater the f-stop, the less light that's going to be admitted. In order to ensure that we have proper exposure of the film emulsion, and the film emulsion is the portion of the film that contains the silver halide crystals, which are these light-sensitive grains. and I'll talk more about that later on. But to have proper exposure of our film, it is important for one to select then the correct relationship between the size of the lens aperture opening, or f-stop, and how long the light is allowed to impinge upon the film plane. So the exposure time is a very important setting in photography in general, and aerial photography specifically, and that is the length of time that the shutter remains open. So shutter speeds usually range from about 1 second, which is quite long, all the way to very short periods of time, 1/1000th or 1/2000th of a second. Now, to increase the amount of light that actually reaches the film plane, one could do a couple of things. We could increase the size of the f-stop. So, for example, we could go from, say, f16 to f11, which would effectively double the area of our aperture opening. Or we could, say, for example, increase the length of the exposure. And if we have an aerial platform, like a plane that is moving very fast, we would typically want to use a fast shutter speed in order to effectively stop action and prevent the blurring of objects that are being imaged on the film plane. Also, if we have environmental conditions that are changing often, let's say due to cloud cover, that can affect the nature of the illumination also within our imaged area. Also, or if the sun elevation is changing throughout the day significantly, that could lead to potentially over or under exposure of our photograph. So as those conditions change, we may need to potentially change the shutter speed. And so we would want to effectively set shutter speed, but also our variety of other aerial photography mission parameters. In terms of the types of aerial cameras, we can summarize them as follows. There are single lens mapping or metric type cameras. There are also multiple lens or multi-band cameras. Panoramic cameras I'll briefly discuss, as well as I will have a brief discussion of digital cameras here, but again, most of this discussion in this lecture is going to be focused on film-based camera systems, just because I'll be discussing in a lot more detail digital remote sensing and electro-optical remote sensing sensor systems in a subsequent lecture. And there's various other types of camera systems as well. Single lens or metric cameras obtain most of the aerial photographs and have obtained most of those photographs historically. Cartographic cameras are calibrated to basically collect the best geometric and radiometric quality aerial photographs. Regarding single lens mapping or metric cameras, those consist of a camera body, a lens cone assembly, a shutter, film feed and uptake motorized transport assembly at the film plane, as well as an aircraft mounting platform. We also typically would be placing filters in front of the lens, and those filters would determine which wavelengths of electromagnetic radiation are actually going to be reaching the film plane. Also note that in the United States, the Federal Aviation Administration, or the FAA, must approve the cutting of a hole within the airplane fuselage that is used to accommodate aerial cameras. So if you have plans on doing something like that, just remember that you need to get FAA approval before doing so. Also keep in mind that the lens cone is going to contain a single multi-element lens that projects an undistorted image of the real world onto the film plane. And this is a cutaway view showing the various internal components of a typical photogrammetric aerial frame camera system. And this is a profile view of a metric camera system with its various components, which may be a little bit easier to visualize in terms of the internal parts of the camera system, maybe relative to the prior slide. But what we see here is the unexposed film reel in the upper portion on the right of this figure, and the film passes across a platen vacuum film flattener while the film is being exposed, while the photons are impinging on the film at the focal plane. And then that film is taken up by the take-up reel. So all of this is contained within that upper portion of the camera system there, what we call the film magazine. We also see in the lower portion of this figure the lens cone assembly, and that contains components such as our multi-element lens, the diaphragm, the filter, so on and so forth. And the shutter system. We also see the lens rear nodal point, and if we measure from that to the focal plane, again, that is our focal length. We also see the optical axis of our camera system denoted there. And also note the filter, again, that is placed in front of our lens system. This is a typical setup inside the aircraft fuselage for a photogrammetric aerial frame camera. So you see the operator positioned right next to the aerial camera system. And this is another example where we have a single camera and a two-person aircrew. And the upper portion of this figure shows a schematic diagram of a one-person aircrew with a single camera system, and the bottom portion shows a two-person crew with a dual camera system setup. This photograph is of the underside of an aircraft in flight that is used for aerial photography acquisition. And what we see are two frame cameras, the portals for those that are mounted within the fuselage of the plane. So again, we have light that is being allowed to pass through from the underside of the plane into our camera system. We have different types of lenses that are used in aerial photography for different types of missions with varying objectives. So we have available to us a narrow lens, for example, and that is where the angular field of view is less than 60 degrees. We also have a normal lens, what's referred to as a normal lens, with an angular field of view of 60 to 75 degrees. A wide-angle lens has an angular field of view of 70 to 100 degrees, and a super wide angle lens has a FOV of greater than 100 degrees. The wider the field of view, the greater the amount of Earth that is going to be recorded on the film at a given altitude above ground level, or AGL. And the higher the altitude, AGL, the greater the amount of Earth that's going to be recorded on the film by each lens. And this is a graphical depiction of what I was discussing. So if we have an aircraft, this is a profile view of the image acquisition, an aircraft that is at a fixed altitude above ground level, in this case, say 1,000 feet, we can change the amount of Earth that is being captured within a given image by changing the field of view of our camera system. So again, if we have a narrower camera lens, let's say a 40-degree field of view, which what we see there, we would be just imaging a pretty narrow swath versus a 90 or 100-degree field of view lens, whereby we would be recording a much wider swath of the Earth's surface there. So changing the field of view of our camera lens is one means, assuming a constant altitude above ground level, that would be the means by which we could potentially alter the amount of Earth that is recorded. On the right-hand side, here we have a fixed field of view lens, but we are changing the altitude above ground level, and hence in effect, we are changing, again, the amount of area that's going to be captured within the photograph that is obtained. So fixed field of view, but if we change the altitude above ground level, we could also change the amount of area that is imaged. So the analogy there would be, again, like if you have a flashlight that is at a certain altitude above the ground level, if you were to increase the altitude of that flashlight above the ground level, the spot size of the flashlight on the ground would be larger. Now, of course, the mechanism of what is going on here is quite different from a flashlight, but the analogy is about the spot size, or the amount of the amount of area over which we are recording information. That's going to change as a function of the altitude above ground level. Another important piece of equipment for aerial photography is an intervalometer, and this is a piece of equipment that exposes the film at particular time intervals. Those time intervals are dependent on the speed of the aircraft as well as the altitude above ground level, and that is going to result then in an appropriate level, ideally, of end-lap, which is end-on-end overlap of the aerial photographs along a flight line that we obtain for stereoscopic coverage. So we want a certain sufficient amount of overlap from one successive aerial photograph to the next along the flight line in order to have stereoscopic imaging, and then based on those data that are being collected, we can derive a variety of products based on photogrammetric analysis. Aerial cameras typically expose film that is 24 centimeters or 9.5 inches wide in rolls of greater than 500 feet in length. That actually depends on the thickness of the film. A typical exposure would be 9 by 9 inches or 23 by 23 centimeters, basically for film that is 9.5 inches wide. Now, depending on the speed as well as the altitude above ground level, the film may be advanced slightly during exposure to compensate for image motion. And in order to do that, we utilize typically an image compensation magazine or an IMC. And an IMC moves the film across the focal plane very quickly on the order of 0 to 60 millimeters per second. And the IMC entails a shifting platen pressure plate with film attached via vacuum in the flight direction in accordance with a velocity to height ratio, or V over H, and the focal length of our lens. So given those camera system parameters and the mission parameters, we would set our IMC appropriately. And the utility of utilizing an IMC is summarized in this figure. We see a visualization of this in the left-hand side with an image that has been acquired actually without image motion compensation. And included within this image we see a swimming pool, a diving board, various other types of objects, including a resolution test target. That's that black target on the ground, black background target with white lines. I'll discuss in more detail what that is later, but essentially it allows us to test or determine the resolution of our aerial photographic system. On the right hand side are those same targets but with image motion compensation deployed. And as you compare the two images, you see that the image on the right is much crisper. You have much better, well-defined boundaries. Again, you don't have the blurring effect that you see on the left-hand side of the figure there. What we see here in this figure is a little bit more than the upper half of a standard aerial photographic print. And around the outside, we see a black border that contains a variety of metadata pertaining to that particular photograph. So included there are things like the altimeter, the time at which the photograph was acquired, the focal length in units of millimeters of that particular camera. That's item number 7 there. We also see item number 4 that I'll call your attention to, which are fiducial marks. Now we only see 3 out of the 4 fiducial marks for this particular photograph, since we don't see the bottom half of this image. But for an aerial photograph, we're going to have either 4 or potentially up to 8 fiducial marks, which serve various purposes in photogrammetry and making various types of measurements from aerial photographs. But the utility of them, in short, would be that if we were to draw lines between opposing fiducial marks, so say, for example, going from the fiducial mark on the left-hand side of the photograph to the one on the right-hand side of the photograph, if we were to draw a line between those two fiducial marks, and likewise, if we were to draw a line between the fiducial mark on the top as well as the one on the bottom we cannot see here in this figure. Where those two lines intersect, though, would be the location of our, what we call the principal point of our image, and we'll discuss the significance of that later on. And this is just a summary of, again, various types of metadata that would be included on an aerial photograph, the annotation around the perimeter of an aerial photograph. So a grayscale step wedge, again the altimeter, fiducial marks, clock, lens cone serial number, focal length of the camera in millimeters, the frame number of that particular aerial photograph, mission, name, date, so on and so forth. terms of other types of aerial cameras, I had previously mentioned a multiple lens or multi-band camera system, and this is just where we have multiple wavelengths that are being sensed, where we're using differing film and or filter combinations in order to acquire our imagery, and photographs with this particular type of setup are taken simultaneously amongst the various multiple cameras. Panoramic cameras, in contrast, use a rotating lens or prism in order to create what is a relatively narrow strip of imagery that is perpendicular to the line of flight. But the exposures typically are going to be vertical just in the center along the flight line and oblique near the ends, or as we are on the outer portion as we extend away from the flight line. For low altitude aerial photography, we pan across the flight line from horizon to horizon, such that we have up to, and this is rather remarkable, a 180-degree field of view. So this is a photograph of a setup that we have for multi-band aerial photography, a common configuration entailing four 70mm Hasselblad cameras arranged in this configuration to acquire four simultaneous photographs. And those four respective photographs that are obtained entail sensitivity to different portions of the electromagnetic spectrum. So as we see on the right-hand side of this figure, a progression starting with the near-infrared portion of the spectrum and segueing to progressively shorter wavelengths. So we have a near-infrared photograph, a red photograph, a green photograph, and at the bottom on the right-hand side is a blue aerial photograph. Again, each one of these are just grayscale images depicting, again, varying degrees of reflectivity in those respective portions of the electromagnetic spectrum. And this is a schematic diagram of a panoramic camera in operation. So again, remember, we see a scanning or a panning across the flight line, potentially from horizon to horizon. Again, a very wide field of view. Often it's a 180-degree field of view. So we see a rotating lens assembly. You also see the direction of flight and the flight line being projected onto the ground there. And again, we're scanning across that. This type of configuration is common in the military, but not so much within the civilian sector. It does not yield very rigid geometry, and again, we're going to have widely varying scale as we go from the image portion of the terrain that is along the flight line versus as we proceed along in either direction toward the horizon. But measuring and mapping are still potentially possible, though, if we are utilizing the required equipment. And this is an example aerial photograph that has been obtained by a panoramic camera. We see in the central portion of the image that portion of the terrain that has been imaged directly beneath our camera system along the flight line. And as we proceed from that area to each of the respective horizons, so to one side of the image as well as to the other side of the image, we see progressively increasing scale variations as well as geometric distortions. Now, in looking at this photograph, we can probably think of various types of military applications and why militaries may often be interested in utilizing this type of imagery. One example application may be, say for example, if an aircraft is flying along the border of a nation state and a given military does not want to fly into the airspace of that particular nation state. Say for example, maybe one does not have permission to fly into that airspace. One could potentially still acquire significant imagery of the ground surface within that nation state by flying a panoramic camera system on an aerial platform along the border. Of course, digital cameras constitute a very important type of camera system for aircraft-based remote sensing. And as I mentioned previously, much of aerial remote sensing has gone over to acquiring images with digital cameras. So with a digital camera, instead of using film, we are using, for example, a charge coupled device or CCD area array. CCDs, one advantage of them is that they are more radiometrically sensitive than silver halide crystals that we have within film emulsions. Again, those are the light sensitive grains within film emulsions. of analog camera systems. So if they're more radiometrically sensitive, we can potentially see greater variability in terms of the albedos and reflective properties of various Earth surface materials in a digital image versus a film-based image. One thing to note is that if we are employing a digital camera system that utilizes a RGB filter wheel, or a red, green, blue filter wheel, or a dichroic grate, at the instance of exposure, the camera records 3 different versions of the scene using 3 filters. A problem with this is that we have essentially successive RGB exposures that are being acquired at slightly different vantage points. And this could translate potentially into differences on the order of hundreds of feet on the ground between the various images. So if this is the case, then the individual image bands are not going to be automatically geometrically registered with one another. And if that is the case, we must use digital image processing techniques in order to register one of those image bands to another. Another potential problem, and this is more so historically the case, is with the spatial resolution. So in order to replicate the spatial resolution of a standard 9 by 9 inch metric camera photograph, one would need 20,000 by 20,000 charge coupled device array in order to acquire an image of a similar spatial resolution. But as digital cameras progress, we're getting successively much higher spatial resolutions possible with these digital systems. So that is much less of a problem today. And on the left-hand side, we see a very commonly used type of analog or film-based camera system. This is a Hasselblad 70 millimeter camera, and this is actually the same type of camera system such as this that were used by the Apollo astronauts in order to obtain photography through the portholes of the spacecraft. And you can even see the little moon insignia on the body of the camera there at the bottom of the camera. On the right-hand side, we see an early digital camera system that this, I believe, is from the late 90s, early 2000s.